Network effects and cascades of adoption, part 3. In the previous two parts, we have seen that systems that are apparently stable may sometimes change radically and extremely quickly, what we call nonlinear explosive change. Nonlinear explosive change may be activated by a butterfly effect. In a butterfly effect, the relationship between cause and effects is strongly nonlinear and the proportionality doesn't exist. Which means that the events that activates the dynamics, which is then powerfully amplified, is non-directly related in terms of size with the consequences that follow. The amplification of the unconsequential trigger is fueled by positive feedback. And we have seen that in the case of VHS versus beta, these dynamics lead to the winner of one standard over standard in a relatively short time compared to the lifetime of the technology. What we're going to see today are different types of network effects. We're going to see how they influence the epidemics, the diffusion of certain information, of ideas, and two fundamental types of dynamics in epidemics of information. Network effects. Network effects are also known as externalities in economics. They are called externalities because they represent factors that influence a transaction without being part of the transaction itself. So they are external to the transaction. Here we discuss a fundamental different viewpoint between two disciplines, let's say economics and sociology. For economics, individuals are decision makers whose preferences are not influenced by other individuals. Whether I like a certain type of food, a certain type of car, or a certain type of behavior depends on my history, on my knowledge, on my upbringing, but not on the context in which I am inserted in. Sociology instead have got kind of opposite point of view, whereby preferences are socially shaped. So they depend on the context, they depend on what other people think, and so on and so forth. We know for certain that under certain situation, preferences are shaped by the social context. Otherwise, there would be no way to explain why market bubbles, why fads spread. We know spreads like piercing or like tattoos or adoption of certain technologies, what we call fashions, are definitely driven by the fact that individuals copy or imitate other individuals around themselves. So to a certain extent, our preferences may be socially shaped. What are the factors that influence the social shaping of preferences? They are classified under three different types of externalities or network effects, which go under the name of information externalities, coercive externalities, and market externalities. Information externalities are factors, information that influence a transaction in absence of the capability of evaluating the transaction directly for the elements of the transaction itself. Let me explain. If you are in a social environment you don't know, you're not familiar with, let's say you move to a new city for your master or whatever, and you need a dentist, you're not able to evaluate the transaction itself, which means the ability of a dentist to solve your problem. So what you do, you resort to some kind of, if you want, tribal mechanism, and you ask your friends, because your friends have a direct experience of the territory. So your decision of the transaction is influenced by the fact that you trust your friends who are familiar with a certain type of environment. That's called that's an example of information externalities. Coercive externalities, the second type, covers a situation in which individuals feel a pressure to conform to the majority. They feel a pressure not to feel isolated. There's a strong evolutionary pressure in our psychology, in our behavior, to follow the majority. We hate, or at least the majority of us hate, being seen as deviant in most situations. This clearly comes from an evolutionary origin in which being left alone by the majority was extremely dangerous. The third type of externalities is called market externalities, in which the value of a certain experience depends on the diffusion, or if you want, the unit of units sold. A classical example is the telephone, the fax machine. Imagine you are the first to adopt a telephone. There's basically nothing you can do with it apart from the status associated with adoption of a new technology. The more the telephone is sold, the more calls you can put. What is interesting is that the diffusion increases linearly, but the number of calls you can put increase quadratically with adoption. This is a clear case in which the value of a good depends on the diffusion of the good itself. This leads to two types of decision making. Absent network effects, decision making is individual. The typical example is the example of friends in a restaurant. Each one looks at the menu and decides on the basis of personal tastes. The opposite situation is a situation in which preferences are shaped by network effects, especially under condition of stress, such it may happen to traders during acceleration of trading time, such as during a crash or during a boom, in which imitation becomes the norm of the game, and individuals may follow the crowd either because imagine that the others have more information, that they know something that they don't know and they don't want to be left alone, or because they see a risk in following their own ideas. And this is the case represented by the famous cartoon of The Economist. The two different decision making, the two different types of decision making lead to different behavior of individuals in a network. The type of contagion is the the social contagion model. In the social contagion model now, the infection is still proportional, still needs exposure, but it's non-linear dependent on exposure. Second, the other thing that matters is the distribution of what we're going to call the individual threshold. Each one of us has got a different sensitivity to pressure exerted by the majority. In this case, context matters, where you come from, your history and the social network features, and how the social network is organized, let's say whether it's scale-free or random or small world, matters. It matters dramatically. And the curve followed by diffusion is not an S-curve, but it's more similar to curves we find in physics during phase transition. We're going to examine all of this in a moment. To explain the social contagion model, we need to refer to a famous experiment done by a sociologist called Solomon Asch in the 60s. Solomon Asch had the brilliant idea of gathering 8 individuals. Psychologists like to play with experiments, and the individuals were asked an apparently very simple question, even trivial or stupid question. The question was, look at the segments in the figure. Look at this figure here, this line here called exhibit 1, and look at the 3 segments on the right hand side. Which of these 3 is closer in length to exhibit 1 line? Now, it should come as no surprise that when individuals are asked individually about this question, all of them basically say A, and it can clearly be seen why. Anyway, what happened during the experiment is that a large fraction of individuals actually gave the wrong answer. How do we explain that? Well, what happened is that around the 8 individuals around the table, 7 of them were actors. and were instructed to give the wrong answer. What happened to the eighth individual who was unaware that the others were actors? When the first individual gave the wrong answer, say B, he in that case thought that probably the first individual needed better glasses, or that he had drank too much the evening before. When the second individual gave the wrong answer, then the subject, the real subject of the experiment, starting being bewildered, asking why perfectly normal individuals that do not seem to be playing and that seem to behave as normal members of normal society, why would they give some clearly wrong answers? Is it something that they know that I don't know? When the third individual gave the wrong answer, then the physiological parameters of the metabolism of the individual started being affected, meaning heartbeat dramatically increased, sweating could be measured, and a clear state of stress was apparent in the subject. Again, the individual at that point starts having doubts about himself, whether it's he that needs glasses, whether even though he thinks that the answer, the right answer is A, whether it wouldn't, he starts feeling a pressure to give the answer A. And in fact, if you look at the curve on the right hand side of the graph, which is the experimental findings that Ash found, is that when the number of individuals before the subject of the experiment gave the wrong answer, and they gave unanimously the wrong answer, then about between 30 and 40% of the subjects starting giving the wrong answer. So what matters here, this is an example of coercive externalities in which an individual, even though might think that the right answer is A, consciously give the wrong answer, whether B or C. What is important in any case is that there is a unanimity among the actors, among the social network of the subject. Because if even one gives the right answer, then the self-confidence of the individual is immediately raised, and there's no doubt that he will give the right answer. This leads to a new understanding of contagion, which is represented in this graph. In a disease type of contagion, a biological contagion, the probability of infection is simply proportional to the number of infected neighbors of that individual. The more you sleep with somebody with HIV, the higher the probability of contacting HIV. The higher the number of people with flu in an airplane at the beginning of the season, the higher the probability that you will contract the virus. What happens in a social contagion instead is different. Let's look at this table here. Here I represent the Solomon-Asch dynamics. On the bottom, on the horizontal line, you find a fraction of neighbors that choose in the wrong length, the wrong segment, over the right segment A. So here you find that the number of individuals choosing the wrong one increases, and all of them give the wrong answer. On the vertical axis, instead, you find the probability of choosing the wrong length from the subject, by the subject of the experiment, the eighth individual. What you notice is that when the number of neighbors of the subject of the experiment is low, the probability of giving the wrong answer is equally very low. And then suddenly, when a relatively high number of neighbors chooses the wrong answer, then the individual switches. Of course, different individuals have different threshold to pressure, to network externality of the type of coercive externality, and this is represented in this graph. Certain individuals never switch. They are so self-confident that basically ignore the opinion of the majority. In this case, this curve never happens, and the probability of choosing option A remains always close to 0. Other individuals are more shy. They really dislike feeling isolated from the majority, and even if a relatively low fraction of neighbors chooses what they think is the wrong option, they follow the crowd. So this switching depends on the individuals. So if you are representing how a society or a social network switches from one option to the other option, then what matters is the distribution of individual threshold. Notice that this curve is very different from this curve. Here, as we said, the probability of infection is simply dependent of number of infected neighbors, so intensity of exposure. Here instead we find a very different behavior represented by a so-called phase transition curve. This is not an S curve. How does this translate into now we go from individual behavior to network behavior? So let's give a very simplified model of this. Let's imagine now that the average threshold, which is, if I take the individual threshold, several individuals, I take the average, and I see what happens in a highly idealized network. Let's say in this case that the individual we concentrate on is called A, or ego, at the center of a certain network. This individual has got 3 neighbors, and the activation threshold of A is 1/3, which means if 1/3 of the social network A is infected with a new idea, A switches as well. It might be a person who likes new technology but doesn't want to take the risk of buying a new technology as soon as it appears. He or she wants to have the comfort of knowing that the technology works and somebody he or she trusts has already adopted the technology. We represent this idea with activation threshold 1/3. So if activation threshold is 1/3, and if this individual becomes active, then A at the next unit of time becomes active. Now let's imagine that we keep the activation threshold 1/3, but now A has got more friends. That means A has got more people to listen to observe. If this number goes from 3 to 4, then what happens? Now, what happens is that in order to achieve activation threshold 1/3, there must be 2 active individuals in A's network. So the fact that now this friend becomes active and say adopts a certain technology is not sufficient anymore to cause a change in A. In other terms, it is if you listen to more people, the influence of each individual decreases. So the more people you have in your network, the less sensitive you become to the words of a single individual. And this model now has got a clear influence on the social contagion model. Now let me introduce a relatively abstract model. This is not very easy to understand, but the ideas are relatively simple behind. On the horizontal axis we represent the average value of the threshold, that is the minimum number of individuals in your network that you need in order to adopt a new idea, in order to persuade it to adopt a new idea. On the vertical axis, we represent the average number of neighbors, which is to how many people you pay attention to. Now, once we have these two information, we can plot the probability that a cascade happens and the probability that such cascade is global, meaning that all the individuals in the social network switch from one state to another state. Notice that the graph is divided in 2 parts. Let's get the blue part and the white part. In the blue part, cascades are possible. In this part here, cascades are impossible because the average value becomes so big, and at the same time the average number of neighbors becomes so large that it's basically impossible that a cascade happens. Why is it impossible a cascade happens? Let's start looking at the lower part of the figure. We consider the case of a network which is sparsely connected. Sparsely connected means that individuals have, on average, just a very few neighbors. Or let's say on average one. On average one means that some individuals may have 2 or 3, but others may have basically 0. If there are 0 connections, it means that certain individuals or certain parts of the network may be fragmented, may be isolated from other parts of the same network. Now, if you're in this condition, that low number of neighbors, the average value threshold becomes irrelevant. Why is it become irrelevant? Because if you just have one neighbor, it doesn't matter how large your threshold is, from 0 to 1, if one person in your network switches, you switch as well. So under conditions of sparsely connected network, individuals in the network are very sensitive to new ideas. Under this condition, the social contagion model and the biological contagion model overlap. They give the same results because neighbors don't matter. Neighbors are so few that that you are exposed to a, let's say, to a virus or to an idea, even though irrespective of your threshold. Under this condition, which we are called cascades at the lower boundary, what happens that, as we said, we are under the condition of sparsely connected network. Some individuals may have many connections, but others on average have 0. This creates a network which is partly fragmented. And then what happens in this network? Because the average value of threshold becomes irrelevant, it means that individuals are easy to be exposed to information, and so the network is locally unstable. So once some individuals switch, the rest switch as well, and this is represented in the central part of this figure. But the point is, because it is a sparsely connected network, that infection, that contagion, remains limited to certain areas. So it's easy to infect a part of the network, but if that part of the network is isolated from the rest, then the network is globally stable. Imagine a situation of villages in a rural part of a country which is relatively isolated from each other. If an infection arrives, then that village is exposed to the network, and potentially everybody falls to a certain virus or bacteria. But if that village is relatively isolated from the rest, the virus may not spread to the whole nation. So that's the condition of a sparsely connected networks, or cascade at the lower boundary, in which the network is globally stable but locally unstable. And in this case, as we said, the biological contagion model and the social contagion model overlap, because neighbors become fundamentally not, the number of neighbors become irrelevant. What happens instead if we examine cascades at the upper boundary? Now, cascades at the upper boundary are cascades in which the number of friends matter. And remember, the more friends you have, the less you pay attention to any single one of them, assuming, of course, an average view. Now, the average number threshold, the average value threshold, becomes important, because now the average number threshold influence whether you switch at a lower number of individuals already that have already opted for another options, or a higher number of individuals. So basically influence whether this curve moves to the left or moves to the right. Remember that now this is how infection happens, and not this curve that represents biological infection probability. So in these conditions, what happens? Now, let's imagine that you are surrounded by several individuals you pay attention to. Let's imagine that the average threshold is still 1/3. If you've got 4 friends, threshold is not exceeded and you don't switch. This means that the more connected you are, the less sensitive you become to new ideas or new information. This is interesting because it's counterintuitive to a popularly held idea that the more connected you are, the more you are, the easier you become exposed to new ideas. But then what happens if, by certain reasons, there's a critical mass of individuals in your network that have already adopted? This is represented here. Imagine now the same conditions are present, the threshold is still 1/3, A sits at the center of social network of 4 neighbors, but by reasons that we don't examine, a critical mass of individuals has switched. Now, so instead A has not 1 active neighbors but 2. Now, because the threshold is 1/3, now A switches, and so now we find this situation. But let's imagine that the network is more complex. So now this is the real network. What happens now? When A switches, suddenly this this node becomes active as well. But when this node becomes active, then this node is exposed to a majority of neighbors that are active now. And then this node becomes exposed and this node becomes exposed. What happens here, in other words, is if we are at the upper boundary, where there's a relatively high number of neighbors, the more neighbors you have, the more stable you are in this current state, because the number of neighbors with the same state lock in a certain situation, block a certain situation. And the more neighbors you have, the more you become convinced or stable in a situation. And conversely, if you are stable because you have got lots of neighbors stable, all the other neighbors are stable because the rest of the neighbors are stable too. But if by random conditions or by certain conditions a critical change is achieved in a fraction of the network that exceeds the average threshold, that generates a global cascade. Now we're in condition, so when we are at the upper boundary, we are under the conditions of a highly connected network. Having many neighbors, meaning that it's extremely unlikely that there are parts of the network that are isolated. This is a very connected network in which individuals are on average connected to many other individuals. So this is, in general, a locally stable network. Why locally stable? Because the more neighbors you have, the less you pay attention to any one of them individually. In order to pay attention, you need to have that a critical fraction of them must have adopted. But that's difficult to happen because the more neighbors they have, the more stable they are as well. So the size of the vulnerable cluster might be small. This is basically determined by the average threshold, but it's difficult to achieve because it's definitely bigger than 1. So cascades here are very rare because the network is locally stable. So from this point of view, this is radically different from biological contagion, because here actually the more surrounded you are by neighbors, the more stable you are, at least in taking a certain decision between 2 states, A and B. So activation here is very unlikely, but if by certain reasons a critical mass or vulnerable cluster, basically a cluster of individuals that exceed the average threshold of that network is achieved, then the contagion spreads as wildfire. Spread as wildfire, and suddenly the whole network switches from A to B. This is what we saw, situation we saw in social networks when nonlinear explosive change takes over, when regimes that have been stable for decades suddenly are toppled. See Tunisia or Libya. When financial markets that have been stable for a long time suddenly go into an accelerated boom or a crash. These are the conditions in which fads, like social fads, spread very quickly, and so on and so forth. So these are to sum up. There are what matters. Individuals in a social network may be exposed to two different types of contagions. In a biological contagion, preferences do not matter, and individuals decide on the basis of their preferences. In a social contagion model, instead, preferences do matter, and the structure of the social network matters. A random network will behave differently in terms of cascade from a small world or a scale-free network. Why? Because the topology, the structure of the network may influence the probability that the vulnerable cluster size is achieved. So a critical mass of change is achieved, which then drives the whole, the transformation, the cascade of the whole network. So social network is different from biological network. In a biological network, contagion is directly proportional to exposure. In a social network, to a certain extent, contagion is inversely proportional to, at least for the beginning of the before the activation threshold is achieved, is inversely proportional to exposure. The curves are radically different. In a biological contagion, we find an S curve. In a social contagion, we find a phase transition, so a sudden change from one state to the other state. In a social contagion, of course, network effects such as cohesive externalities become extremely important. They are irrelevant in a biological contagion model. In terms of reading, again, this stuff of cascade is very well explained in this book by Duncan Watts. I've already pointed out that book. It's the top book to understand cascades of information. Gladwell as well talks about similar points, but Gladwell ignores or doesn't pay enough attention to the difference between social and biological contagion model. The other articles or books are also interesting.